In this video, I will be going over the Chapter 7, Day 8, and Day 9 notes, which cover applications of exponential growth and exponential decay. Now recall, exponential growth starts off at a low value and increases over time, and that's because the base is going to be greater than 1, whereas in exponential decay, it starts off at a high amount but gets lower over time, and the key here is that the base is a fraction or decimal between 0 and 1. So many natural phenomena have been found to follow the law that the amount varies over time according to the following exponential relationship. And we're going to say that this is a sub t equals a sub 0 times e to the kt power, where k is a value that is greater than 0. You've actually seen this exponential relationship before. It looks different, but when we did investments, we had the PERT formula. The amount equals P times E raised to the RT power. This is the exact same model, but it just uses different variables. So you might want to write this part down, but a sub 0 is your original amount. Just like in our investment problems where P was the amount that we invested, A is going to be the original amount. K, instead of the R, is a rate or a constant for the problem, and it's different for every problem you do. And T is going to be time, but the base is E, just like in the PERT formula. So we're going to be using our calculator for all these problems. But even though it looks different, we're going to use the exact same steps to help us answer some questions. So for this first one, we're looking at the size of an insect population, and they actually give us the equation to model that growth. It says P equals 500 times E to the 0.02 t power. Now notice the 500 stands for that a sub 0. And so that 500 is the original amount of insects, or the starting population for this problem. So then part A says, if we start out at 500, how many will we have after 10 days? So I'm going to plug in the 10 for the time. So it just looks like this. And so then I'm going to find my calculator here and enter that and see what I get back. All right, so 500 second ln 0.02 times 10, hit enter, and we're talking about insects and population, so I probably can't use a decimal, can't have part of an insect, so I'm going to round up to 611 insects. So after 10 days, it grew by 111 insects. Now for part B, it says, well, how many days will it take for the population to actually go to 1,000? So after 10 days, it's 611, but how many days will it take to go to 1,000? So this is going to look a little different. It's going to be 1,000 equals 500 e to the 0.02 t power. We actually need to solve this for t. This is an exponential equation. To solve an exponential equation, I need to get the base by itself. E is the base, so I'm going to divide both sides by 500. 1,000 divided by 500 is 2. And now what happens is, usually I would try to get bases to be the same, but since the base is E, I can't do that. So then I'm going to take the log on both sides, and because my base is E, I'm going to use the natural log. Now I use the log on both sides, not only because I can't get bases to be the same, but then I'm going to use the power property, and I'm going to put that power out front. So it's going to be the natural log of 2 equals 0.02 t times the natural log of E. So a couple things happen here. First off, we know that the natural log of E is just 1. Anything times 1 doesn't change, so that drops out. And that's the really nice part when the base is e and we use the natural log. But the other thing is I'm going to divide by 0.02 to get t by itself. So here it is. It's the natural log of 2 divided by 0.02. So I would close the parentheses around the 2 and then divide. And I can have part of a day, so I'll just round it to the nearest tenth. 34.7 days. So it takes 34.7 days for the population to reach 1,000. So then in part C it says, well, same idea, how long will it take to reach 2,000? So I have the following formula. I'm going to divide by 500, which 2,000 divided by 500 is 4. And I'm going to take the natural log on both sides. And then I will move the power out front. And the really nice part is the natural log of e is just 1. So then I will just divide by the decimal. And you'll notice that my work was the exact same. The only thing that changed, it was a 2 up here, but now it's a 4. So then I'm going to just change that in my calculator to a 4. And that answer is 69.3 days. So then this last part, what does the 500 represent in the original equation? Well, 500 was a sub 0, and that represents the original population of insects. All right, so this is a really good example of what we're looking at here today. When they give you the formula, you can either plug in the time, or more than likely, in part B and part C, you're going to solve for the time, which is going to require you to take the natural log on both sides. But you get to divide that 500 first before you do that. The work that you see here in part B and part C, we're going to see over and over again. So let's go to the next page. Another example of exponential growth is cell division. That's a universal process, and under ideal circumstances, you can model this with an exponential relationship. So I'm going to use that same idea that we wrote on the front page here. Number 2, a colony of bacteria increases according to the law of inhibited growth. This is just another way of saying exponential growth. If the number of bacteria doubles in 3 hours, find the value of k and express n as a function of t. So sometimes they use n instead of a for the amount or the number of things present. So if you want to just change that n to a capital A, because they're talking about this. A of t is equal to a sub 0 times e to the kt power. That's the model that we wrote on the front of the notes, and so they just want us to find k. So I know that the number of bacteria doubles in 3 hours. They don't tell me how much I start with, though. So if my original amount is a sub 0 and it doubles, then I will end up with 2 times a sub 0. And it takes 3 hours for it to double. So I can plug a 3 in for t. We can actually solve this for k. So if I divide both sides by a sub 0, they're going to cancel out. So I don't actually need to know the starting amount because it doubles. So this 2 is the important part. So I have 2 equals e to the 3k power. In order to solve for k, I have to take the natural log on both sides. So once I take the natural log, I can move the power out front. So that would be natural log of 2 equals 3k times natural log of e. Now we know that the natural log of e is 1, so then all I have to do is divide by 3. So I'm going to take natural log of 2 divided by 3, And I'm going to use quite a few decimal places here just to make sure that my final answer that I use for part B and part C isn't too far rounded. So if I use 3 decimal places, K is around 0.231. So try to use at least 3, if not more, so that way your answers for part B and part C are more accurate. You know, if you were just to say 0.2, then your answers are going to be way off for part B and part C. So then I guess what I would write is a sub t equals a sub 0 e to the 0.231 t power. But basically, they just wanted us to find that k value. So part B says, how long will it take for the colony to triple? So if it doubles in 3 hours, how long will it take it to triple? Well, tripling means to take the original amount and multiply it by 3. But now I'm actually going to use this k value that we found, and I'm going to solve for t. So a sub 0 is the same on both sides, so I have 3 is equal to e raised to the 0.231 t power. So the 3 is important because we're tripling, so we don't need to know the original population. So then natural log of 3 equals natural log of e to the 0.231 t power, and then I'm going to bring the power out front. And once again, the natural log of e is just 1. So just divide by that decimal. And this is time, so decimals are allowed. It's going to be around 4.76 hours. And so the way that this works is you're using natural logs quite a bit, and you just have to figure out, like in part A, we're solving for k, but in part B, we're solving for time. The key is they didn't give us the initial amount. So when you see doubling, we're thinking of the number 2. Or if we see tripling, then we're going to find and use the number 3. And part C says, how long does it take for the population to double a second time? Well, it's going to be the exact same time that it took to double initially. It'll just take another 3 hours for it to double again. And you could go through that work, right? So if you wanted to put in a 2 and do that work all over again, you definitely can. Or you can just kind of use some logic here to help you decide what that would be. So here's what I mean if you wanted to do it by hand. So if I change this to a 2 instead of a 3, if I take the natural log of 2 divided by 0.231, notice you get 3 hours. So you could work that problem out again, or maybe use the information from part A. Let's go to the last page. So the last page here is going to talk about exponential decay. Okay, so exponential decay is going to look very similar to what we've been talking about. A of t equals a sub 0 times e to the k t power. But the difference is that k is going to be a negative number, not a positive number. And the best example of an application of exponential decay is radioactive decay and half-life. So you may have talked about this in a science class previously, but half-life, every radioactive material has a half-life, and it is the time that it takes for half of the radioactive substance to decay. So materials that are radioactive are unstable, and because they're unstable, they decay over time. So scientists use their half-life to help measure a certain amount of time based off of how long it takes for the substance to decay. And one application of that is carbon dating. So this is a technique that compares the amount of carbon-14 present in an organism during and after life to determine the date of death. And so all of this is closely related because it's all exponential decay. So let's go down to the example here. Strontium-90 is a radioactive material that decays according to the following equation, where a sub 0, of course, is the initial amount, and a is the amount present over a certain amount of time. It says, what is the half-life of strontium-90? So once again, they're not giving us the initial amount of material, but they're saying that there's going to be half of it left over. So this is very similar to the doubling or the tripling situation. Half-life, I take half of the original amount. And then I just go ahead and copy down the model that they gave us. So half-life is half of the original amount. The original amount goes away. So then I have half equals e to the negative 0.0244 t power. And guess what? You're going to take the natural log on both sides. And this process just kind of repeats itself as we've done it quite a few times today. So you will get t is equal to the natural log of a half, which you'll want to put in parentheses, divided by negative 0.0244. That's going to give you how long it takes for half of the substance to decay. And that should be around 28.4 years. So once again, if you see half-life, the number you're going to use here is a half. And last one here, determine how long it takes for 100 grams to decay down to 10 grams. So here they're actually giving us a starting amount. And it's going to, over time, reduce down to 10. So the way that this would look would be like this. So this is more than one half-life. So if I was considering the half-life of 100 grams, 100 grams would go down to 50. And half of 50 would be 25. And half of 25 would be 12.5. So we're seeing quite a few cycles of a half-life to get down to this 10 grams. But I don't even have to think about it like that, because if I put 100 in for the initial amount and set it equal to 10, because this is where I want it to end, I would divide by 100, and that would be 0.1 is equal to e to the negative 0.244 t power. And I'm going to fast forward to the work that I did over here. You would just get the natural log of the number out front divided by that decimal. Okay, so I'm skipping some steps there because they're the exact same. It's going to take 94.4 years. So the half-life is 28.4. Notice we did a couple half-lives, so this number should be much bigger. And there is your video for today.